come to the summary of the first activities around the relative values of heating, cooling and electricity demands and powers. This is the building under study, an office building located in the Netherlands, a temperate climate. The simulated hourly loads are shown in the figure. The nominal heating load is 421 kW, the nominal cooling load is 921 kW. To obtain the annual energy use, you need to sum up all hourly energy amounts. Excel did that for you, and you got an annual heating energy of 854,052 kWh and an annual cooling energy of 297,505 kWh. Please note that the scale is not identical in both graphics. Heating goes up to 500 kW, while cooling goes to 1000 kW. The peak load for cooling, 921, is much higher than the peak load for heating, 421. However, the space heating is on most hours of the year, while the cooling demand is restricted to summer months. Let's look more in detail at this. While the annual space heating demand is much higher than the annual cooling demand, that's the left picture, the reverse is true for the powers, that's the right picture. This is very typical of moderate climates. The peak for heating is not high, but there is a continuous demand for heat. The peak for cooling is high, while the demand for cooling is limited to a few weeks a year. As the investment costs relate to the nominal power, cooling will need a relatively high investment, while it will not be used often. That is why taking measures to reduce this high peak is recommended. An example of such a measure is the use of external solar blinds to reduce the peak in solar gains. Let's now look at the relative sizes of heat demand and powers for space heating and hot tap water. Our building is an office building. That's the left bar in both figures. Obviously, both the heating energy and the power for hot tap water are very low in comparison with what is needed for space heating. That is logical, because little warm water is used in offices, generally only the sinks in the lavatory. That is the reason why we asked you to convert the building into an apartment building with 129 apartments and to look at what happens then. That is what you can see on the right bars of both pictures. The energy demand for hot tap water is around 20% of the total. As for the power, it is clear that hot tap water needs a lot of power, more than 80% of the total. This high power is needed to heat the water rapidly. You don't want to wait 10 minutes that the tap or shower water finally becomes warm. But in the end, you don't need warm water that often, so the energy demand is low. This is completely in line with the practice in temperate countries. The hot water boiler of a house will generally be 18 to 30 kW, while the space heating boiler will be only 4 to 7 kW. Let's look now at the ratios of electrical and thermal energy demand. The electrical demand, in yellow, is more than 50% of the total demand. This is logical in an office building with a lot of lighting and appliances. When developing alternative designs to minimize the energy demand, you will observe that minimizing the one often increases the other, and that a balance must be found between all. Additionally, don't forget that this does not say something about your annual energy costs or about the primary energy use. For this, you will need to choose the energy supply, that is the subject of another course. Thank you for your attention.